Three, two, one. All right, here we go. Back at it with some pre-recorded videos. Hopefully the last set, but life finds a way. So, all right. Plot for today. We are going to establish the recursive formula for determinants. So we've instead of starting with this, we've instead established that there is a unique function from the set of n by n matrices to the real numbers, satisfying the following three key properties. First, it's identity preserving, meaning that the identity maps to 1. It is alternating, meaning that the determinant is equal to 0 whenever our matrix has two identical rows. And furthermore, it is row linear, or multilinear, or n-linear, whatever you want to call this, but it's linear with respect to the rows, meaning that the determinant is a linear function when our matrix C has a linear combo in the corresponding rows of A and B, where all the rows are held fixed. So if we have a matrix where there is a row with a linear combo, then the determinant will act linearly. All right. And as we know, this is sort of the meat of the determinant here. Similar to row operations, right? This immediately conjures up that, hey, this looks a lot like the aftermath of a row op, so it should interact nicely with it, hence why this would be sort of the right thing to look at. Alright, so as we noted, you can start with the recursive formula and then go through the very arduous task of proving everything about it. It's not fun. Or we can take this approach where we just say, alright, there's a function, it's got these properties, life's good. And along the way of establishing all of the wonderful facts, you will also establish the uniqueness in existence. Now, we've already proven uniqueness, and the way we got there was by establishing, of course, all of the classic determinant formulas. The determinant of a scaled matrix is the scaled determinant, where the scalar picks up a n, the number of rows, because, as we noted, the determinant, when you scale a matrix's row, will scale the determinant by the row linearity, so if every row is scaled, we pick up n copies. The big one, the determinant is non-zero precisely when my matrix is invertible, which then let us prove that the determinant of a product is the product of the determinants. Again, the x of the y is the y of the x, our favorite phrase in mathematics. As a consequence of this, we think that the determinant of a inverse of a matrix is 1 over the determinant. A nice little formula there. And, of course, the determinant of a transpose is the determinant of the original, which, again, as we noted by their knowledge of the recursive formula, this has to be true because doing the recursive formula across the rows or the columns should give us the same thing. So the determinant should not be affected by transposing. There are children yelling downstairs. I don't know what they're mad about, but we'll see. All right. Okay, and again, the way we got all of these was by using the row linearity to establish that the determinant of an elementary matrix times a matrix is equal to some non-zero multiple of the determinant of the original. And as we saw in the proofs of all of this, that alpha is dependent only on the matrix E. What type of elementary matrix it is determines what type of scalar shows up there. So that means that if there is a determinant function, it's got to be unique because, right, the matrices E are independent of the determinant, so their behavior is, right, unaffected. So if there is a determinant function, it has to be unique. So the uniqueness we've gotten taken care of.
Can I fix a movie?
Not right now.
Okay.
Okay. Alright, the movie is apparently not working correctly. Alright, I'm gonna have to fix that in between recordings here. Anyway, back into this. Alright, yeah, so again, we've now established the uniqueness, so if you have any alternating row linear identity preserving mappings, if you have a pair of them, they have to be identical. And again, that comes from this because this alpha depends only on the matrix E. It does not depend on the fact that the determinant has the nice properties it does. So, all right. And in class, we specifically wrote out the actual proof of that. So the uniqueness is down, so we know that if there are determinant functions, there can only be one. Now, of course, their task is to establish the recursive formula. Now, we proved that for the set of 2 by 2 matrices, the magic number AD minus BC, this mapping is row linear alternating and identity preserving, so in particular, it must be the determinant on the set of 2 by 2 matrices. Okay. And it is worth noting, before we get to that notation, it is worth noting that this will ensure the existence of the determinant function for all sizes, because once you have the recursive formula, right, we know it works for 2 by 2s, so we can get it for 3 by 3s then, and so on and so forth. So, yeah. So, as we noted, we are just asserting there is a function that is unique and is alternating row linear and identity preserving. We've already established that it has to be unique, and now we'll get the existence. All right. Now, as we already discussed, the recursive formula involves deleting a row and a column, so we need some notation for this. And again, this is a not agreed upon notation. I do our matrix A to the P comma Q to indicate that I'm deleting row P and column Q. There's not a particularly standard notation for this. Some people will use subscript, which again is against our principles, because our subscript notation is for the entry of the matrix. So you got to make a decision. It is worth noting that just like row operations, deleting rows and deleting columns can be represented using matrix multiplications. We don't need that for the proof here, so we're not going to do that, but if for the interested listener, you can go ahead and actually figure out the matrices that you need. Spoilers, you just delete the row and the column of the identity matrix and then multiply. But if you are interested, there's a way of representing this without having to introduce a special notation, but it's a lot messier, so I'm not going to do it. All right, so first step we're going to do is not quite the full-on recursive formula, but instead what we'll demonstrate is that a certain mapping is row linear. In particular, the mapping, and I have an n+1 artifact hanging out over here. Let me fix that. As always, there's always something wrong in the slides. There we go. All right, so our first step in getting the recursive formula is actually to kind of focus in on the major piece of it, which is you delete your row, your column, you compute your determinant, and then you multiply by the entry. And as we're going to see, that process of deleting a row and a column, computing the determinant, and then multiplying by the entry is a row linear action. So in other words, any mapping that does that must be row linear. And so finally, as we noted, the recursive formula, you can just present that to somebody, but why do you delete the row and the column? Why do you multiply by entries? Why is there a plus and minus nonsense going on? Well, here we're going to see the deleting the row and the column and the multiplying by an entry is to ensure that the row linearity is there. All right. So we're going to do this step first before we introduce the summation and the pluses and minuses, this will isolate sort of why you delete row and columns and why you multiply by entries, and reveals sort of why we need that in the context of row linear. Good stuff. All right. And similarly, on your problem list, I'm going to make you prove something is row linear where you're multiplying the entries of a matrix. So this is a good one to pay attention to if you want some help with that homework problem. All right, so let's set it up. I want to prove that this mapping is row linear, so that means I need a matrix where a linear combo is happening in a row, and all the other rows are uninteresting. So we got a trio of matrices A, B, and C, where row J has the linear combo, and all the other rows, nothing is happening. All right. So what do we need to look at? Well, I need to show that T of C is equal to alpha times T of A plus beta of T of B. All right, I want to show it's linear with respect to the rows. Now, what does my mapping do? Well, it deletes a row and a column, computes a determinant, and multiplies by an entry. My matrix C only has something interesting happening in row J. So there are two cases I got to look at. When the row I'm deleting is the row with the linear combo, and when the row I'm deleting does not involve the linear combo. No. So there's just two possibilities we need to break into. All right, so suppose that the row that's deleted is not the row with the linear combo. All right. Alright, gotta fix this. Alright, then the matrix that is formed by deleting the row and the column of P and Q respectively will still have a row with a linear combo, and thus the row linearity comes into effect, because the determinant of C with row P and column Q deleted will have a linear combo in some row. It may not be J anymore, it might still be J, depending on if we delete before or after J. But regardless, there'll be a linear combo, and so the determinant pulls it apart as according. The CPQ distributes. We pull out the alpha and the beta, and we note that, hey, P is not equal to J, which means that the matrix C and the matrix A are identical in that row. Likewise, the matrix C and the matrix B are identical in that row. Aye, what's going on with this parentheses? Jesus. That's decided to flip around for no good reason. Let me fix that. Yeah, this one right here. What's it doing? Ooh, look at that magic. All right. Anyway, so here we see why we need to have the multiplication in place. Well, not quite exactly. Well, we just see that you kind of need the multiplication to go along for the ride here. But right, the multiplying of the entry, not quite clear why this is necessary. But with the row linearity, we see that kind of just goes along for the ride, and this pulls apart accordingly, and the entry just goes along for the ride. So, alright. The row linearity preserved, even if you do delete the row in the column. Here we see that if the row is the one that is not deleted, then just row linearity carries across the determinant, and the multiplied by the entry just is there. Alright, so that's one part of the problem. The other part is what happens if the row that is deleted is the row with the linear combo. Alright. Well, if that happens, then all three of those matrices are identical, because we deleted the row where something was happening, and all the other rows are the same, so these are all the same matrix. So now we see why you needed to multiply the entry, because this is now the one where the linear combo happens, so this acts linearly, right? You get your linear combo, now you multiply your determinant out, pull the scalars across, and then as we noted, this matrix is the same as these, so those come into play. And now we see the reasoning for why you have to multiply by the entry of where the row and the column is deleted, because otherwise the row linearity does not carry across, because if you deleted the row where the linear combo is, the determinant's not going to know what to do. So that's why this multiplication needs to happen. So there we see right, the two cases breaking down and showing us why we need these two components of deleting row column, and why you need multiplying by the entry. Right, the row column needed here for when the linear combo is not in the deleted row, so the determinant can act linearly. And here, multiplying by the entry is needed to ensure that the row linearity actually goes down, because without it, we don't get our linear combo. Alright, there we go. So we have now proven that deleting the row in the column and multiplying by the entry grabs us the row linearity. Now we just need to throw in the plus and minus thing that we know, and that will give us the alternating and the identity preserving, and we're going to be very happy about this. Alright, and again, I have this n plus 1. Now note something about what we're actually proving. We're proving the recursive formula for columns, actually. We're not starting with the row factorization, we're dealing with the column one instead. We'll get the row one because, of course, transposing does not change the value of a determinant. Alright, and let's see, man, what is going on with these slides here? Alright, let's fix that. Okay, there we go. Alright. So, we'll prove that this is identity-preserving, alternating, and row linear, and thus that would mean that this mapping right here has to be the determinant, and thus we get our recursive formula. Alright, so first we'll note the row linearity comes from the previous prop. We know that this right here, the highlighted term, is row linear, and if you linearly combined row linearities, you get something that's row linear. In the same way that if you combine linear mappings together linearly with scaling and adding, you still have linearity. Second of all, the identity preserving is also essentially for free, because if you put the identity matrix in here, and if you look at all the formulas carefully, the KQ entry of the identity matrix will be 0 when K is not equal to Q. So the only thing that shows up is the Q term. The identity matrix's QQ entry is 1. So that does not make an appearance here. Here we'll have negative 1 to the q plus q, so that's negative 1 to an even number, which means that it will equal 1. And if you delete the qth row and qth column of the n by n identity matrix, you'll get the n minus 1 by n minus 1 identity matrix. And of course, the determinant of that is 1. All right. So the only thing we actually have to verify is the alternating property. And with that, we're happy. All right, now it's worth noting that for the alternating property, the only thing we actually need to establish is that the matrix T of A is equal to 0 for matrices that have two adjacent rows that are identical. From that, any two matrices that have two identical rows, well, then you can perform a bunch of row ops and get something that is equivalent to it. So it turns out that you actually only need to get the adjacent rows to 0 out, which is a nice little feature here. Right, so then you can just swap the rows to get it for any two identical ones, because we know that for row linear mappings, swapping two rows will just simply negate it. So we only need to prove this for adjacent rows. All right, now note for such a matrix, the determinant of the kth row and qth column deleted will equal 0 whenever the kth row is not j or j plus 1, because we didn't delete the two identical rows, so the determinant must equal 0. And moreover, if you delete the jth row, or if you delete the j plus 1 row, then you'll have the same matrix, because this matrix had two rows that were identical, specifically these two adjacent rows. So then if we go to our formula for t, it deletes everything except for the jth and jth plus 1. And now we see the power of the negative 1 coming into play, because, hey, j plus 1 here, well, we just cranked it up 1, and you can pull off one of those extra negative 1s. And because the jth and jth plus 1 rows are identical, these will break down like this, and oh, wouldn't you know it, this just so happens to 0 out, so our mapping is indeed alternating. And now we see the alternating property, why you need the pluses and minuses, because we need the adjacent terms to be able to cancel each other out here. And life's good. There we go. So, all of the ingredients for the recursive formula are now clear. The deletion of the row in the column and the multiplying by the entries guarantees the row linearity. The summation of all of these things guarantees row linearity, and the plus and minus is there to ensure the alternating goes through. And of course, the identity preservation just comes through with the formula, so we're happy about that. All right. And now we have demonstrated uniqueness, and the existence now is guaranteed because we've proven how to create larger determinants using a previous determinant. And again, we've got this plus 1 nonsense going on. That's just coming from previous versions. All right. Anyway, so we've now established the following beautiful recursive formula. So pick a column, go down it, pluses and minuses, multiply by entries, delete rows and columns, take the determinant. And there you go, the recursive formula established. All right, so that's the one for columns, and now the one for rows is easy peasy, because the determinant of a matrix is equal to the determinant of a transpose, and if you just pop the transpose into this formula, you'll get the rows. All right. Beautiful. So there we go. The recursive formula for determinants now established. There we go. So there is a unique, alternating row linear identity preserving mapping on the set of n by n matrices. We now have a formula to compute it all. We know how to do it for 2x2s. It's the AD minus BC. And now for larger size matrices, it can be computed recursively as follows. All right, sweet. So there we go. We have established the determinant's basic properties. And now we've got the classic recursive formula for it. So what's the goal for the next video? Well, we're going to put the recursive formula to work and establish the formula for the inverse of an n by n matrix using something called the adjugate. And then while we're at it, we'll also talk about another oldie but a goodie, good old Cramer's rule. So that will be the next video.